Hello everyone, in this video I'm going to explain some examples about power series solutions to linear equations. And I think the most important point first is to understand if you have a form, and of course let's say the coefficient is a function of x, for example, and the second derivative is a function of x, and let's say do this way. I think by now you know how these work. So let's say you have this differential equation, and we need to put it in the standard form, and that's by dividing you divide by the first coefficient here, which is a sub 2 of x, and that would lead to the second derivative of function of x plus some p of x times the first derivative that is a function of x plus q of x times the function y, let's say equal to 0. So we know what p of x is a sub 1 divided by a sub 2, and q of x is a naught divided by a sub 2. So we say that let's say definition, but kind of abbreviated in a way. We say x naught is an ordinary point, which I'll write as pt later, if both p and q are analytic at x naught. Is an ordinary point if both p and q are analytic at x naught. So what if they are not? Then otherwise I think maybe a quicker way to abbreviate this. Otherwise x naught in the case where x naught isn't, we will say it is singular point. All right, of the equation. Alright, so some x naught is an ordinary point if both this p and q are analytic at x naught. If it isn't, then it is singular a point of the equation. And I think some of them are easy to find, but let's give you an example that mixes different things. So let's say x times second derivative plus x over 1 minus x, the first derivative, plus let's say sine of x times the function equals 0. And let's find this analytic and singular points. So here if we divide by x, then p of x will be this, and q of x will be sine of x over x. So initially, as we know in the past, when you look at functions, you'll say now x as 0, x as 1, and here x as 0, and we start to investigate. But what really happens is p of x can be simplified and now the issue is x equal 1. So that's a singular point, because p is not analytic at this x naught that is 1. Of course, here you see divided by x equals 0 is going to be an issue, but we know that sine of x can be kind of defined as a power series. So if you try that, what will happen for sine of x as a Taylor expansion? We can do this you've seen in calc. Then you divide by x. So what happens is actually x can be simplified. So x divided by x is 1. Then this is x squared divided by 3 factorial plus x to the 4th divided by 5 factorial. So what happens is actually this is analytic everywhere. So it's analytic everywhere, right? It doesn't have that issue. So really which now we can call this, maybe they'll use different color, just like you've seen in calculus, removable discontinuity. So this is a removable singular point. So now the only singular point here of this equation, only singular point is x equal 1. Yeah, so this kind of example kind of gives you everything at once. Then the other examples you usually encounter may not have all these other details. So let's give you one to think about. All right, so so think about this one. And you're going to say I'm going to divide by x plus 4. Then that's going to make p to be this times y prime and q to be this times y equals 0. So yeah, so we do have a singular point at x equal -4. Let's say you have this type. So you're going to divide by t squared minus t minus 6, and you have t plus 2 and look, let's say so t plus 2, the factoring of that is going to be t minus 3 and t plus 2, and the factoring here is plus 2. So 1 over t minus 3 and 1 over t plus 2. That still keeps the singular points to be the 2. So singular points here are negative 2 and 3. Alright. Let's do one where maybe you don't have any, because not necessarily you're going to have singular points. Let's say this. Using the knowledge we know for exponential, it has an asymptote, horizontal, so it can't be 0. So when you divide by e power x, then no singular point. Alright, because just the cannot be e power x cannot be 0. Okay, so I think now I'm gonna do an example that will actually put everything together for you as far as the summation, and we've seen, if you looked at other videos, how to combine, and I'm sure you've done in calc before, but I talked about how to add summations and stuff. In this example, we're going to look into all those skills and put them together to find a power series that is a solution to a linear equation. So let's say in this example we're going to need to solve this x squared plus 1 let's say plus 10 times second derivative plus y equals 0, and we need to find, let's say, the 4 first terms that are of course non-negative terms, non-negative in a form of power series. Expansion. In a form of power series about, let's say, about some, let's say x equals 0. Yeah, let's pick that one, x equals 0. Of course, what you need to understand is here is going to be for a general solution. So when you do this, the more terms, of course, the better, but you'll see that they are enough what we're going to find, but that describes a general solution. Alright, so here, before I go to the next page, you see if you divide by x squared plus 10, that can't be 0, so analytic everywhere for this one. And that solution, this general solution is described, maybe write it as y of x with this series n equal from n equals 0 to infinity, and it's going to be a sub n times x power n, right? So this is kind of what we are interested in. And as you see here, you have a second derivative. So using the previous work that we did, so you say, what is the first derivative? Yeah, it's just going to be n from 1 to infinity, a sub n, and the power rule, n times x minus 1. Then from there, what is the second derivative? Then of course n now from 2 to infinity, a sub n times n minus 1 times x n minus 2. Alright, so now just like we've done in our previous kind of work before, so we will need to take this here and put it there, right? And take this here and put it there, right? Substitute. Then we need to find something that will allow us to equal to 0. So we will force the coefficients and the left hand side pretty much to be forced to equal 0. So this equation is satisfied and we can find the solution. So all these, they start this way. The only tricky part is how to deal with summation, and you're going to see some nice techniques there, and this is useful to do because in some work, of course, like engineering and stuff, you deal with these summations and you need to know how to put them together. Alright, so let's put the second derivative in that form that we found. Then plus the function. Alright, so now let's distribute. So this times that, and this again times that. Alright, so the first one, a sub n times n minus 1, this times x squared. Then the next one is just times 10. Alright, then now we do this last part. Alright, these are xn, no changing remaining term. Then we saw in the past that we need to, in order to put these together, we need this is n minus 2, and this is n, and this is n. So the n's work, and we can just put k for them, but this other one we need to introduce a new variable, which is k. So k is n minus 2, which makes n to be k plus 2. So if this is k, and if n is equal to 2, then k will start from 0 there, right? And this will be k plus 2, and this will be k plus 2 minus 1, alright? And these we can just say k. We can just put k for n. and k for a. All right. Um, so here k equal 2 to infinity a sub k times k minus 1 x power k. This one changed from k equals 0 to infinity, 10 times an or a sub n, so a sub k plus 2, this is k plus 2, this is k plus 1, x power k, and this is just k. Alright, so we have good progress. So now we do have so I want you to ask the question. We do have this, we have this, we have this, so we can do we can combine, except we have a problem. What do you think the problem is? Yeah, you see it? The problem is k. These two can kind of like naturally think can work together, but this one doesn't. That's not 0, so we cannot put them together. But we do, you know, from what you know in the past, we can try to make this k equal 2, or actually make these others k equals 0. It's k equals 0, 1, 2. K equal will go right, and so forth. So k equals 0, 1, 2, and keeps going. So what we will do is we will rewrite these as individuals and leave the summation to start from k equal 2. Same thing here. I will kind of like extract the first term of k equals 0, k equal 1, and leave the summation to start from k equal 2. And that will give me summations that start with k equal 2, and they have x power k. They can be put together. Then I have some leftover terms from this 0 and 1, and everything will work out towards the end. All right. So that's what I will do. So now you can pause the video and try it. So if k equals 0, and now replace, then you will have ak plus 2, that'll be a sub 2 times 10 times 2 times 1 times x power 0. Then a sub 3 times 10 times 3 times 2 times x. Just show you here because we moved to the next page. So here, so I did this here, right? Then I did 1. Then I will go to this one next. Alright, so now I'll go to the next one. You do this, that's that, and you do this, and that's that. Okay, so now what's going on? We have the summations all start with k equal 2. Then I have those terms I calculated for k equals 0, 1, and the other for k equals 0, 1. Alright, so here, yeah, let's finish these. 10 times 2 is 28, which is, this is a naught. Maybe I need to give some space here. This is a1, and that's gonna give us 68.3. Alright, and these are just unfinished. Alright, so the first one was 28.2. The next one was 68.3 times x. I forgot x here. Alright. Then this one is just that. And this one is just that. Equals 0. Alright. So that's the equation. After we substituted, we made everything power k, and we needed to make everything start from k equal 2. So we have 4 additional, they're not additional terms, but just 4 terms that are not in the summation, and here they are. So now what we need to understand is where this left side is equal to 0. When is that going to happen? It's going to happen when this left hand side equals 0, right? So you know that here I have x power k, so I can combine these and factor out x power k. When I factor out x power k, its coefficient needs to be 0. That's one thing. So let's just make sure A3 has x. Let's just make sure I complete all the terms. So here I took that one, I took this one, I took this, so the 4. So now you also have seen from pre-calculus all the way to this course that if you have, let's just look into these, right? That's they have x, so a1 plus 68.3 power x, and these don't have any, so a0, a or a naught or a sub 0 there, plus 28.2 are together, right? So these must equal to 0, and this coefficient must equal to 0. Then the coefficient that's going to be with this x naught here must be 0 as well. So let's write this summation here. So k equals 2 from 2 to infinity of this a sub k times k minus 1 plus 10 a sub k plus 2 times k plus 2 times k plus 1 plus a sub k all x power k, right? So this also, this coefficient must be 0. Alright, so when you factor x power k, its coefficient must go to 0. The other coefficients, that everything that's on this left side must equal to 0. We factor x, so this coefficient a sub 1 plus 68 a sub 3 must be equal to 0. Alright, so that kind of give us, I'll leave it in this place so you can see what we will get. So this one here, it will give you, let's say, let's say a sub 3 is a sub 1 divided by 60, or a sub 1 equal negative 60 a sub 3, right? This one here, same thing. A sub 2 is negative 1 over 20 a sub 1, a sub 0. Alright, then you'll say, what am I going to do with this big thing? Usually you will solve for this. So let's write it down and we solve for it. Alright, so that coefficient, the big one, and it is the coefficient of this, let's rewrite it. That goes to 0. I have to here of sub k, this I can put together. Then I have alright, so you're going to kind of write this here in terms of we have this times a sub k there, and of course you'll divide by 10 times k plus 2 times k plus 1. Alright, so based on this formula, let's say you're looking for, of course you start with let's say 0. Then if you do a for k equals 0, then you get this, then plug it 0 and you get 1 over 20 a naught. And if you plug in 1 for k, you get negative 1 over 60 a1 or a sub 1. Alright, so we have a kind of an idea now about the solution. So the solution, or the general solution, that y of x, it's gonna be, now you're gonna say where this come from. Let's go back. Here, you see it. So when you write this, it's gonna be what? A naught x power 0 is just 1, then a sub 1 x power 1, right? A sub 2 x squared, and we keep going, right? So that's, now we'll express the solution. So expressing the solution, a sub 0 or a naught is a naught, a sub 1 x, what did we find? We found a sub 2 here to be that, and we found a sub 3 to be that. Alright, so I'll replace them. So that's gonna be negative now. X squared, and you can see as well from there 60 a sub 1 x cubed, and 1 2 3 4. So we found the first 4. All right, so you can see how the process works, and and it just repeats. Okay, thank you.